So now let's derive an expression for electric field at any general point due to an electric dipole. So for that we need a diagram. Suppose these two circles represent charges constituting the dipole as minus q and plus q. Let's name them as charge A and charge B, and let's join their central line as this, and let's make an inclined line from the midpoint of this dipole, and we'll place that general point somewhere on that inclined line. So suppose this is the point where we need to find out the electric field due to this dipole. So say this point is some q, and also the distance of this point from the midpoint of the dipole is say represented by r. So this distance is r, meaning from here to here is say r, and this is the midpoint represented by O, and the dipole moment of this dipole would be along this line, as it is always directed from negative to positive. Now if we drop a perpendicular from the center of charge B to this yellow line, we can obtain a right angle triangle, and thus if this angle is theta, then we will have P's component, one along this line and the other one along this line. Say this one I name as P1, and this would be like P cos theta, and same way this one I name as say P2, it would be represented as P sin theta. And as far as the electric field at this point is concerned, it would also have two components, one along the axis and the other one perpendicular to the axis, so somewhat like this, and the resultant would be along this line, say ER. So say this electric field is represented as E1, and the perpendicular one is represented as E2, and the angle between them is say phi. So here we can write E1 is along the axis, and from the previous derivation we know electric field along the axis due to an electric dipole is given by 2k dash P1 upon R cube. Here P1 is P cos theta, so this will be 2k dash P cos theta upon R cube. So this is the electric field along the axis at that point, and same way E2 is along the equatorial line. Therefore from the previous derivation we also have equatorial lines electric field due to a short dipole, so that is given by k dash P2 upon R cube. Here P2, as we can see, is P sin theta, so we can replace that P2 with P sin theta whole upon R cube. This is our electric field at the perpendicular axis at that point. Now as we can see, the angle between the two electric fields E1 and E2 is 90 degrees because they are perpendicular to each other. Thus, and the electric field is also a vector quantity. Thus we can write down ER, the resultant electric field, as E1 square plus E2 square plus 2 E1 E2 cos of some delta, because theta and phi we have already used, so we will use some different symbol, and theta over here is 90 degrees and cos 90 is 0. Therefore E resultant would be simply E1 square plus E2 square. Now substituting the values of E1 and E2 in equation 3, say this is equation 3, what we get, meaning say put 1 and 2 in 3, so we'll get ER as root of 2k dash P cos theta upon R cubes whole square, plus k dash p sine theta upon r cubes whole square. So now this we can write as square root of k dash p upon r cubes whole square into 2 cos theta square plus k dash p upon r cubes square into sine theta square. Now we can take this term common from these two, and since they are already square, so we can take them outside the root. So this would be k dash p upon r cube into root of 2 cos square theta would 2 cos theta's whole square would be 4 cos square theta plus sine square theta sine theta square. And we also know that cos square theta plus sine square theta is 1, the basic trigo identity. Thus we can write this 4 cos square theta as 3 cos square theta plus cos square theta plus sine square theta, and this quantity is nothing but 1. So therefore ER as expression we can write as k dash p upon r cube root of 3 cos square theta plus 1. So this is the final expression for electric field at any point due to a electric dipole. Now we have find out the electric field, but what is the inclination of that electric field? So meaning we need to find out this angle phi. So I'll draw the diagram again. Say this is the diagram, this is ER, this is angle phi, and this is E1 and this is E2. So if we draw a right angle triangle over here, so we can say this represents E2, and if we take tan of phi, so tan of phi would be like opposite by adjacent, so it would be E2 by E1. And from the previous expressions, equation 1 and 2, E2 and E1 we can replace. E2 is this and E1 is this one. E2 is k dash p sine theta upon r cube, and E1 is 2k dash p cos theta upon r cube. This is like tan phi. Now a lot of things would get cancelled over here. Say r cube, k dash p would cancel, and ultimately the terms that we would be left with is tan phi is sine theta by 2 cos theta. So that is like half. Sine theta by cos theta is nothing but tan theta. So this is tan phi. One of the expressions. We can also write phi as tan inverse of this whole thing, which is half tan of theta. Along with the resultant electric field, this is the expression for the angle of that resultant with one of the electric field.